Has the secret of the Hubble pressure at last been tackled? The fact that the universe is expanding quicker than it should, in principle, is one of the most noteworthy secrets in space research. However, now specialists from the universities of Bonn and St. Andrews have found something that could lead directly to the solution of this annoying galactic problem. Our Milky Way might be situated in a massive void and, therefore, in an especially empty region of the universe. And lo and behold, as soon as we apply an alternative hypothesis of gravity, the disparity between the theoretical and actually measured expansion rate of the universe can be made sense of, basically. Sadly, however, there is a little catch to this momentous approach. It is an obvious inconsistency with the cosmological standard model, which has for some time been part of the essentials of space science. Today marks something of a significant change in perspective. Around quite a while ago, for ages, specialists of the past were convinced that the universe was an unbending, perpetual construct. Even a certain Albert Einstein initially clung to the idea of a static universe, so much so that he added a cosmological constant to his equations, a step he later regretted as the greatest blunder of his life. And although the young Belgian cleric and astrophysicist Georges Lemaitre had already shown Einstein, in 1927, how a numerical model describing an expanding universe could be created from the general theory of relativity, Einstein dismissed this concept as a mere mathematical trick. Nonetheless, we know that Lemaitre's discoveries had a conclusive benefit. After all, they made a prediction that could actually be observed explicitly. It overcame any issues between the expansion of the universe and the light from galaxies. If the universe is truly expanding, the other galaxies in space should be moving away from us, just as the dots drawn on an inflatable move away from one another when it is inflated. Similarly, the light from the galaxies would be stretched on its way to us, and the frequencies would be stretched. The light that reaches our naked eye would eventually be shifted into the red. And indeed, in the late 1920s, the American astronomer Edwin Hubble was able to prove just that. The relentless observation of many galaxies at the Mount Wilson Observatory in California showed that the light was, indeed, redshifted, and the expansion of the universe was practically recognizable. However, this situation was also connected to a no less revolutionary reversal. If the universe is continually expanding, then, seen in reverse, it should also have had a beginning, a minuscule point from which everything once arose. And while that minuscule point is now at the core of the theory of how things came to be, in the 1990s, astronomers realized that the universe isn't just expanding, but that its rate of expansion is also increasing. Dark energy is believed to be the strange main driving force behind this speed-up, an unfathomed power that is expected to counteract the force of gravity, the strange Hubble pressure. So, why is the universe growing quicker than it should? A crucial center of the vast expansion puzzle, however, consists of the question of how fast the universe is expanding. In theory, it is demonstrated by the so-called Hubble constant. However, in practice, the specific determination of this value has led specialists into a field of confusing deviations, collectively known as the Hubble strain. According to the standard model, the Hubble constant should be around 67 kilometers per second per megaparsec. To put this into perspective, 1 megaparsec is about 3.26 million light-years, and 1 light-year is 9.46 trillion kilometers. In other words, this means that the speed at which the galaxies in space move away from one another increases by 67 kilometers per second every 3.26 million light-years. That's a remarkable 24,400,000 kilometers per hour per megaparsec. However, it may be fundamentally quicker. As already mentioned, these are only the theoretical expectations, but when we determine the value of the Hubble constant through direct cosmic measurements using supernova gravitational lenses, variable stars, or red giants, it suddenly sums to 73 kilometers per second per megaparsec. That's again 264,000 kilometers per hour per megaparsec, and thus an error of an incredible 20,000 kilometers per hour per megaparsec. But how could this significantly higher value be explained? Is it conceivable that previous examinations were defective with adulterating estimation blunders? Well, This was unequivocally the question that the James Webb Telescope tended to when it examined the information from the Hubble telescope in the course of new perceptions. Explicitly, the exploration group led by Nobel Prize-winning physicist Adam Rees of Johns Hopkins University in Baltimore zeroed in on the data that Webb had gathered over the past 2 years. Since the capacities of the most current space telescope ever far surpass those of its logical ancestors, specialists say that it shows us the universe in HD, so to speak. Thus, the specialists had the option to partake in a razor-sharp affirmation of the Hubble tension. The assessment of the largest Webb dataset to date, which included supernovae, variable stars, red giants, and a class of carbon-rich giant stars, showed that the universe doesn't in fact act as anticipated by the theory. As a result, the general outcome this time also yielded a Hubble constant of 72.6 kilometers per second per megaparsec, and as indicated by Rees, the inconsistencies between the anticipated and observed development rates literally shout that our understanding of the universe is basically deficient in such manner. It's possible that we have, up until this point, ignored a part that gave the young universe an unexpected motivation later, the Big Bang. Besides, it could also be that dark energy is changing. For example, it is denser or more intense today than in the prior vast parts. It should be noted at this point, anyway, that analysts are also talking about alternatives to the impact of dark energy, and one of these is based on the interesting thought that the Milky Way, alongside our Earth, is situated in a large void. Is the Milky Way caught in a supervoid? To understand what this huge void is about, we first need to review the all-encompassing structure of the universe. As is notable, stars and planetary systems are tracked down in galaxies, which in turn combine to form galaxy clusters and then structure superclusters. For quite a while, specialists saw the largest intelligible structures in the universe in such superclusters. However, the huge scope studies showed that the superclusters are in no way, shape, or form randomly distributed in space, but rather organized in a network-like design. The cross-section of this structure is framed by lengthy filaments known as fibers, which can be several hundred million light-years across. In the same breath, the fibers all also range immense, for all intents and purposes without matter, bubbles, the purported voids. Despite the fact that the daily perspective on the atmosphere looks like an abundant cosmic scene, a few specialists expect that these pits even make up the greater part of the universe. Expressed in calculates, this implies that an expected 50 to 90% of the universe is described by a yawning drain of issue. A study led by Sergei Marrow of the University of Bonn now suggests that the impact of the voids might directly lead to the formation of the expansion enigma. The study, completed in collaboration with researchers from the University of St Andrews in Scotland, is based on a new observation showing that the Earth is in reality situated in a region of space with a somewhat minimal amount of matter, similar to an air bubble heated into a cake. Thus, the density of matter around the air pocket is much higher, and gravitational forces radiate from it, pulling the galaxies inside the air pocket close to the edge of the hole. What sounds both simple and conceivable could eventually amount to just that. Thus, the galaxies are moving away from us faster than one would in fact expect. In this setting, the deviations of the Hubble constant can therefore be explained simply by a nearby underdensity, a simple explanation, but one that has a little, yet essential, catch. The standard model doesn't accommodate such underdensities or voids by any means because matter and space should really be equally distributed. They shouldn't exist by any stretch of the imagination. But then, how can the 600 million light-year distant galaxies be explained, for example, which were examined by another research group and are receding from us multiple times faster than the standard model of cosmology permits? Well, in this manner, Pavel Kupa, who was also involved in the void study, states that the standard model is based on a theory of the nature of gravity proposed by Einstein, and that gravitational forces might act uniquely in contrast to what the maker of the theory of relativity anticipated. Specifically, the research groups at the universities of Bonn and St Andrews used a modified theory of gravity in their virtual experience. The adjusted Newtonian elements, or M for short, was proposed by the Israeli physicist Mahi Magram nearly 30 years ago and is still considered an outcast theory today. But Magram predicts the presence of enormous void air pockets in space, And that is precisely the key point. Since, if gravity really acts as Magram believes, the issue of the Hubble pressure would vanish in one fell swoop. And since the observed deviations would be due to abnormalities in the distribution of matter, there would indeed be just one constant for the expansion of the universe. Alternatively, anyway, this would also imply that we would need to forsake the laid-out theories of Newton and Einstein about the nature of gravity. Kupa complains that this is precisely the imposing research obstacle. More specifically, the astrophysicist refers to areas of strength for the anteroom of established theories, which has a significant effect on the distribution of research funding. Approaches that test long-established thoughts are often dismissed as crazy or informal, which is why it's even more difficult to obtain funding from the major councils. Our advisory committee has just approved your free membership. We'd be happy if you click approval and hit subscribe now so you won't miss a new video from us again. We'll see you soon.